Okay, so we're on our log functions. Again, we've seen this before in the last chapter. Sorry, I have a bit of laryngitis here, so we'll struggle on. Okay, so a log function is of this form: y is equal to the log of x to the base a, where a is a positive constant. So basically, that base is a positive number. Um, a log function is the inverse of an exponential function. So we've seen this before as well. And one is a reflection of the other in the line y is equal to x. And again, we saw that in the exponential chapter. But just before we continue, we'll just recap on that. So, like, if we base this on what we did in the last lesson, we in this case here, we're looking at where x is bigger than 1. And they're basically saying that if that's your exponential function, then that's your log function, and they're inverses of each other. Okay, we're going to talk a bit more about inverses in the next video, but that's, one is the inverse of the other. They are connected. So if a is positive, here we have our exponential, and we expect it to look kind of like a tick, and it absolutely does. Then this here is the line y equals to x. Now, why is it called that? Well, because no matter where you go on that line, that will be the point 1, 1, that will be the point 2, 2, that will be the point 3, 3, 4, 4, 5, 5. So in other words, no matter where you go on that line, the y value equals the x value. So that's why it's called y is equal to x, because everywhere along that line, you have the x and y coordinates being the same. Now, if you were to fold along this pink line or this red line, the pink graph would print like as if that was wet ink, that if that pink was wet ink and you folded it along the red line, you would land down on top of the blue line. So what we're saying is the blue is a reflection of the pink. So in other words, the log is the second graph. And remember when we were doing this the last time, I said I always think of the log graph to look like the branch of a tree, which makes sense because logs come from trees. So think of our exponential is our tick or our slide, and our log is our branch of a tree. So that green one is the log, and the other one is the exponential function, but they are inverses of each other. So the one is a reflection of the other in the line y equals to x. Now, what happens then if our exponential, if the a is negative, not negative, a fraction, I should say, fraction is less than 0. Now, if it's less than 0, we expect this to be a slide. And there it is. Okay, so that's what we would expect to see for that exponential function. Now, again, if you imagine the blue to be wet paint and you fold that along the y equals to x line, which is the line where all the x and y values are the same, 1, 1, 2, 2, 3, 3, 4, 4, minus 1, minus 1, minus 2, minus 2, minus 3, minus 3, you will see that that would print onto the blue one. It would print on exactly to the blue one. So again, one is a reflection of the other. So we saw all of that before, but maybe we understand it a bit better now because of the way the graphs look. So let's remind ourselves again, we did do this in the last chapter. How do we graph logs? Now, the graphing of logs is a little bit different. When we go to do our domain, instead of doing our usual 0, 1, 2, 3, for example, we don't do that. So what we do is we take the base number 2, and then we put 2's everywhere, and then it's the power that's the 0, 1, 2, 3. So that's a really big difference than any other graph we've seen. For the other one, the base is 3, so I'm going to put 3's everywhere. And then I put my, now I'm choosing 0, 1, 2, 3. You could choose anything there, but I'm just choosing, kind of just your standard 0, 1, 2, 3. Now, when you put that into your function, so this is the function, you end up with this. So in other words, wherever there's an x, you then put in your domain. So you're putting in this and putting in your 2 to the power of 3. Now, the whole point of doing what we just did was that you end up having matching log and base. So remember, the power comes to the front. So really it is 0 times 1. Why 1? Because matching log and base. You have matching log and base everywhere, which is exactly why we do what we do. So the 1 comes to the front, so you end up with 1 times 1. The 2 comes to the front, 2 times 2. The 3 comes to the front. Any matching log and base is 1. So you end up with 0, 1, 4, and 3. No, that's not right. I have a 2 there. Sorry, I should have a 1 there. I was thinking something doesn't look quite right. Sorry, so it should be 2. Right, so my couples are 2 to the power of 0. So 2 to the power of 0 is 1. So my first couple is 1, 0. My next couple, 2 to the power of 1 is 2. So I'm putting my domain and my outputs together, my inputs and my outputs. 2 to the power of 2 is 4. So that's 4, 2. And then this one is 2 to the power of 3 is 8, 8, 3. So if I plot that, 1, 0, or sorry, 1, 0, 1, 0, 2, 1, 4, 2, and 3, 3. This is what, no, 4, 2, 8, 3, 8, 3. So we connect them up. Now this graph, sorry, it's just quite narrow, so it's kind of looks like a straight line. It's technically not, but it is, like a branch. It's supposed to look like a branch. It just looks a bit, it's very steep there. It looks very steep, but it's not a straight line. So make sure you put that curve in. Make sure that curve is there so that it looks kind of like a branch. I'm going to continue this in the next video because if they get too long, I can't put them on YouTube. So I'm just going to stop there.